it was due today. So I did earlier.
Nope, not due today.
It was the grossest thing.
Nope, challenge problem due tomorrow.
How late will you be here at this school? Because I don't know if I'll make it back to school, but my brother, I have to come back to my brother.
It was disgusting.
Okay, well, if you want my help after school, you'll see me at 2:40. Okay, I'm not going to play the game where I'm going to sit here and wait for you while you do your workouts and go drop people off and so on. Okay. If you need help otherwise, give me a call at home or come see me early in the morning. All right. Good morning. Last time we got together, we were dealing with these rotational quantities. Let's take a quick gander. Let's see if I can, oops, excuse me. One thing I'm missing here is my cute little display. Polyvision icon strip. There we go. Yes. All right. Okay, so last time we got together, we were on part 2, the angular quantities. Okay, we've got our first angular quantity, which is angular position or rotational position. Theta in radians. Okay, we define the radian as linear distance or arc length over radius. And we went through that analysis on Friday, so hopefully that's still in your head somewhere. It allows us to go from linear measure to angular measure and back again very easily. All you got to do is know the radius. Okay, we define theta just as the angular position relative to the positive x-axis, and of course, angular displacement delta theta is just theta final minus theta initial. Okay, part B, angular velocity. Okay, as we said, symbol is the Greek letter omega. Looks like a curvy little lowercase w. Now, back in the day, linear velocity was just dx dt. So you might guess that rotational or angular velocity is going to be d theta dt. How fast your angular position is changing. Now, back in the day, we also said that average velocity is delta x over delta t. So if you want, you could also say average angular velocity is delta theta over delta t. But the official definition is the calculus one. Now, question, is angular velocity a vector, do you think? Darn tootin' it is. Now, the hard part, though, is determining the direction in a way that's consistent. So, for example, if I take my bike wheel of doom here and start rotating it, it's got an angular velocity. How would you describe that?
How fast it spins.
Yeah, but how would you describe the direction? Clockwise, counterclockwise. Pick a point on it and say, okay, it's got a certain linear velocities, therefore, okay. So all good thoughts. The problem with clockwise, counterclockwise is you and I would get a different answer, right? Here's another problem. Here's an angular velocity. Folks, here's a different angular velocity. All right? Angular velocity, I can actually feel that it takes a little effort to change this angular velocity from one direction to another. So angular velocity is a thing, and it depends on the orientation of the wheel. It depends on, which way you're looking at it from. So what we have to do is get rid of all of that. So we come up with a convention. And the beauty of this convention is that it works. Okay? Here it comes. Take the fingers of your right hand. Curl them along the axis in the direction the wheel is spinning. So your fingies point in the direction it's spinning. Your thumb points in the direction of the angular velocity. The right hand rule. So let your thumb be your guide. So the thumb actually is pointing straight through Stephen's head. This is the direction of the angular velocity. So if I spin it the other way, oh, it's going right through me. If I do this, it goes right into the ground. Do this, right into the sky. Okay? Think of it right now as a convention. Asking why do we do this is like asking why do we drive on the right-hand side of the road? Because we had to pick a side, right? Otherwise, we all die. So we've got to pick some way of finding the angular velocity. Okay? That will make sense. By the way, when it's spinning this way, be careful you don't stick your thumb in the spokes because that hurts. Of course. Okay. So right-hand rule determines the direction of the velocity. And again, if you've ever unscrewed something, a bolt or the top off a, I don't even have one here, top off of a 2-liter, you know that when you rotate it this way, yeah, there you go, which way does the top go? And when you rotate it this way, which way does the top go? Okay, so we have right-hand threads on our screw tops most of the time. And so they follow the right-hand rule as well. So you've been doing the right-hand rule your whole life, you just didn't know about it. Yes, Lucas?
It's off topic and
All righty. Thank you for prefacing. All right, so in my notes, I just have, it is a vector, direction determined by the right-hand rule. Whoops. R-I-G-H-T, hand rule. Some days. Okay. Nextly, we have to be able to go from linear velocity to rotational velocity in a snap. And guess what? We can do that because we've got this little puppy up here. Now, if theta is x over r, is our definition of radian measure, then delta theta equals delta x over r. Or, if I divide each side by delta t, I've got delta theta over delta t equals delta x over delta t over r. I just decided to divide the numerator by delta t. Or I've got, whoops, omega equals v over r. Let's see if that shows up. Either I lost communication or something happened. Well, that's a fine how do you do. Okay, let's try this again. Okay, I probably pressed the little tiny button on the side by accident. Oh, look at that. Woo! Okay, so what that little guy means is that if I know how fast something's spinning, I can tell you how fast it's rolling down the street. Or, if it's rolling down the street at a certain speed, I can tell you how fast it's spinning. All I need to know is the radius. So, for example, where'd my bike wheel go again? Let's say this half-meter radius bike wheel, I'm told that the little sensor on board, as it rolls down the street, is telling me that it's turning at 20 radians per second. Okay, so if it's turning at 20 radians per second, that's the omega. I also know that the radius of the wheel is half a meter. So if omega is V over R, V is omega times R, and the need for radian measure becomes really pretty clear. Uh-oh. Uh-oh. Pardon me. Oh. Sorry, whoever's listening to this recording. Okay, so 20 radians per second times half a meter. Wait, I'm going to get 10 radian meters per second. Ooh, but, ladies and gentlemen, what's a radian? The top distance is measured in what?
Meters.
And radius is measured in what?
Meter.
Meters. So radians are the ghost unit. A meter per meter is not really a unit of measure. My stiff professors in college would say radians are a dimensionless quantity. So I call them the ghost unit. When we need it to disappear, it goes away. And we have left meters per second. We actually do have a linear velocity out of this. Okay? You all right with that? Because radians are just meters per meters, or inch per inch, or feet per feet. Okay? League per league. All right, so radians are kind of weird. We put them there to keep us sane, but they really don't have any dimension. They're just ghostly little guys we set there just to keep us from, like, losing it. Okay, that's everything about angular velocity that you ever need to know. Next, angular acceleration. So I'm going to do a quick erasure here. Let's see. Yeah, just hit the X, right? Bam. It's all gone, except for my chicken scratchings. You okay, Steven? All's good?
Yep.
Got them all caught up? All right, part C, angular acceleration. Alpha. Okay, units. What do you think? Say it louder.
Meters per second.
I love it. Radians per second squared. Why is that giggling out there? Radians per second squared.
I may have said meters.
Oh, you said meter. I'm sorry. I thought you said
No, I
radians.
said radians.
Yeah, you said radians. We'll rewind the video. I thought for sure you said radians. It's just what I wanted to hear, wasn't it?
Yeah.
I'm sorry.
That's hey, imagine.
Imagine that. What'd you say?
Imagine. I wish you'd do that on that test.
I'll just hallucinate when I grade your test. I'll say, that Jake is so smart. This is what he meant to say. Right? I'm sorry. You're kind of quiet this morning. All right. So, remember, good old acceleration is dv dt. So, our new acceleration is going to be d omega dt. How fast the angular velocity is going up or going down. Again, average acceleration, if you want to go back to last year, we would have said delta omega over delta t, the change in velocity over time, but, you know, the official definition is the calculus one. Okay? Also, direction determined by the right-hand rule. It's a little tougher, because what you have to do is think about how the omega is changing. So we've got little guy here where the red dot go. There we go. Little guy here hanging on to the edge of my wheel. I make my wheel go faster and faster and faster and faster and faster, and he will have an angular acceleration this way. But once he gets up to speed, I could slow him down. He'll have an angular acceleration in the opposite direction. Okay. The other thing to keep in mind is when he's doing this, okay, he's accelerating. He's got a linear acceleration that's getting bigger and bigger and bigger and bigger. And so his velocity gets bigger. His acceleration then can be translated into a linear acceleration. So just like before, grab the wrong pen. Just like before, we could say, look, if theta is x over r and omega is v over r, could we say that alpha is a over r? Yes. We could figure out what this little guy's linear acceleration is as the wheel starts going faster and faster, faster, or slower, slower, slower. With one little problem. Question. What if this thing had a constant omega? It wasn't speeding up or slowing down at all. Would the little red dot have an acceleration? Do objects that are moving in a circle have an acceleration? You darn tootin' they do. It's got an acceleration toward the center. It's called its centripetal acceleration, yeah? So, if this thing is speeding up faster and faster and faster and faster and faster, it's got an acceleration this way, tangent to the wheel, along with the acceleration it always had, which is toward the center of the wheel. So, there's a little bit of fly in ointment here. It's a little serpent in paradise. Here it comes. This is actually tangential acceleration. It's tangent to the circle. We always have a radial acceleration when the wheel is spinning. And remember, the radial acceleration, sometimes called the centripetal acceleration. In this chapter, they call it radial, just to confuse you. So centripetal acceleration, radial acceleration, same thing, v squared over r. Now, v is a linear term, right? That's how fast in meters per second he's going around. I could do a quick-o change-o here and say, look, v is omega times r, and stick that in for v. And so I could say omega squared r squared over r is centripetal acceleration. You okay, Jake? All I did is replace the v with omega times r. But look, I got an r squared on top and an r on the bottom, so wah! It's omega squared r. So one way to say radial acceleration is v squared over r. Another way to say it is omega squared times r. So this little guy can have two accelerations. So as he goes around the circle, if it's speeding up as it goes, he's got an acceleration this way. But because he's going in a circle, he's got an acceleration this way. And if I wanted to, I could calculate the resultant acceleration, right? The two accelerations can come together, and I could do a quick Pythagorean theorem, inverse tangent, and discover what the net acceleration is. It's a weird thought. So here's radial acceleration, the centripetal acceleration, and here's the tangential acceleration. Notice that if there is a tangential acceleration, then a sub r is busy changing, right? Because the faster it goes, the bigger the acceleration toward the center. Okay. So I have just unloaded on you a whole lot of new variables and new equations. So it would only be fair if I try to summarize all of this into one big, beautiful thing. Okay? So here's the story. We could write this up as the next, Lord of the Rings novel or something. We have two realms. The realm of the linear and the realm of the rotational. Set betwixt these two realms is a giant chasm which no one can cross unless you have the magic equation. So, on the linear side, we've got position, velocity, acceleration, each being the first derivative of the previous one. So if you want to call this guy dx dt and this guy dv dt, cool. On the other side, we have a parallel realm here where we've got theta, omega, and alpha. And if you want to call this guy d theta dt, and this guy d omega dt, no problem. Now, we can cross the chasm by using our definition. Oh no! I didn't mean to do that. There we go. That's better. We can cross the chasm by remembering our equation for the definition of radian measure, which was theta is x over r. Or x is theta times r. So the equation that allows you to jump from one side to the other is x equals, come on, theta times r. And for v equals omega times r. And for a, we've got a sub t equals alpha times r. And again, we say a sub t, what's that? That's just the tangential part. The radial part is v squared over r, or omega squared times r. So that bridge is a little bit shaky, but we can handle that. Okay, so in a nutshell, that's everything we've done, including some of the stuff we did back on Friday. Now, yes, sir?
Why did they pick the Greek symbols they did? Is there any reason for that? Or did they
Well,
just, like, graphically random?
The idea here is that this is the same stuff, but in a rotational world. So alpha, for example, is the Greek letter lowercase a. Okay? Omega is about as close as we come to a Greek letter V. And theta is just used for angle all the time. So we use theta instead of x. But yeah, the idea was to give it the same flavor as x, v, and a, except Greek letters instead of Roman letters. Yeah. So it kind of makes sense. In my weird brain, it makes sense. But I've seen this a couple of times. Now, what's kind of cool about this is back in the linear realm, we have these cute little equations that work for us. For example, the final velocity of an object. Well, that was weird. Okay. The machine has again lost its mind. Hang on just a second. Whoa!
Goes.
All right. So apparently, something has taken over. We'll try this again. All right, I'm just going to ignore that. I'm going to try to ignore that. It's creeping me out a little bit, but I'm going to try to ignore it. We've got this cute little equation that says V final equals V initial plus A delta T. Yeah? You've seen him before. Well, guess what? In the world of rotation, omega final equals omega naught plus alpha delta T. In other words, you want to find out how fast something's spinning. You got to know how fast it's spinning to begin with, and then you can add on the effective acceleration. It accelerates at so many radians per second squared for so many seconds. It's the same calculation. It's just applied to rotation. We also have this cute little guy. How far something goes, its displacement is V naught delta T plus 1/2 A delta T squared. If we go to the rotational world, we'd say delta theta equals omega naught delta T plus 1/2 alpha delta T squared. I know it's kind of weird looking, but it works. So if you want to know how far something has turned while it's accelerating, use the Dragon equation on it. And then, of course, we have the time-independent equation that says, and you'll love this, V final equals the square root of V naught squared plus 2A delta X. Instead, we will say omega final equals the square root of omega naught squared plus 2 alpha delta theta. A very famous sorority in college, Alpha Delta Theta. I won't go any further. Okay, so we've got a whole range of equations which we've already derived, we already have used. We're just going to apply them now to the rotational world. So I have a few examples. I came up with 4 examples. I added one last night because I wasn't concerned, but we'll see. Maybe we won't need it. So we might need only 3 examples. We'll see where we're at. Oh, by the way, I have the examples as handouts here. So if you're attempting to take notes and, you know, things are going fast on the screen, these are the examples we're about to do. If you don't want them, use it as scrap paper. If they help in your note-taking, go before it. Go back.
Will we be getting more equations to add to like this?
Oh, of course. Yes. There's a whole realm of rotational equations. We have to translate everything we know now into rotational terms. Kinetic energy, momentum, F equals ma. It's never ending.
Is that all going to be on one test? Or
Oh, it will. Yes, we're going to take both chapters and put them on one test. Yep. It's going to be epic. Epic. So you don't want to miss any days in the next little while here. Do your best.
Oh, that sucks for Amanda. She's still gonna stop trying to
Well.
come back from that.
She'll have plenty of help. All right. So let's do a couple of examples. I put this up on the screen here, but I'm going to erase it now. If you need another copy of this, I do have a copy I can send you that's really nice. But I do have to clear the screen right now. So hopefully it's in your notes. If not, I can get this to you. All right. So don't do that. I think it's going insane. There we go. All right. I'm just clicking on the video. That's funny. Okay, back to being able to draw. Okay, it seems to have stabilized. Okay, the first one. The flywheel's angular position is given by this crazy equation. Find its angular acceleration at t equals 2 seconds. And you would say, oh, child's play, right? Because I have the equation for theta. How can I find the equation for alpha? take the derivative twice. Yeah. So I'm going to say, all right, d theta dt, aka omega, is going to be 8t cubed plus 12. And d omega dt, aka alpha, is equal to 24t squared. Stick your 2 in there. What do you get? 96 radians per second squared. Did you say radians per second squared this time? Okay. I just didn't imagine that. See, I just have great faith in you, Jake. That's all there is to it.
So you have to have the omega and alpha.
I can't tell what you're saying, Bree.
So you have to have the omega and alpha after the d theta dt or no?
Not really. I just put it there to make that clear. You could leave these guys off and just say, hey, look, omega is 8t cubed plus, you know. However, having those there, remember that challenge problem by saying that the derivative was equal to a certain quantity, that was worth a point. So, you know, I'm trying to be AP-like when I'm doing this. Yeah, good question. Very good question. Okay, second example. All right, go to the full erasure here and get out of drawing mode. Move to the next slide. Go back into drawing mode. Interesting. Okay, a wheel spins according to omega equals 6t squared plus 5. Find omega, or I beg your pardon, find theta as a function of time if of the wheel if when t equals 1 second, theta equals 8 radians. So here's a guy who could walk to work barefoot on grass. So I've got the function for omega. I want the function for theta. What do I do? Take the backwards derivative. Couldn't have said it better myself. What do we call backwards derivatives? Integrals. Yeah. So I'm going to say, what? Why are you laughing at Bree?
Backwards derivative.
That's exactly the right answer. Backwards derivative. I mean, we give it a special name. We call it integral, but that's really all it is, yeah? So what we're going to do is we're going to say, okay, well, I can find theta. It's going to be the integral of omega of t dt. Okay, so I'm going to say, oh, okay, this is 6t squared plus 5. That's the cream filling. And this is going to get me theta. Now, I have to ask you a question. Oh, let's take the backwards derivative first. The backwards derivative is going to be, okay, I'm going to raise the t to the third power and divide the coefficient by 3. So I've got 2t cubed. Okay, here this is 5t to the 0th power. So I'm going to raise the t to the first power. So I've got 5t. Now, there's a hiccup here. How many of you are taking calculus this year? Most of you. Okay. Here's the hiccup. Remember what I said? You could always figure out if you did it right by taking the derivative of your answer and seeing if that you get back the original. And so if I take the derivative of that, I get 6t plus 5, and I'm pretty happy. But what about this? If I take the derivative of that, do I get my original back? Crap. What if this were 86? Do I get the original back?
Yep.
Okay. The problem is an integral without limits, without the little numbers top and bottom, is called an indefinite integral because it has an infinite number of right answers. I could put any constant here at the end and this thing would be right. So the way they handle this in calculus, this little problem, is by doing this. Let's see, I want to go back to beautiful. It's by putting a plus c there. Because really, there are an infinite number of c's. I put any rational number in for c, and I've got a potential answer. But in physics, we can't leave things hanging off like that because we're trying to mimic reality with this math. But notice what they do. They give us some info. They say, hey, for this particular function, when t is 1 second, theta is 8. Okay, so when theta is 8, I'm going to stick 1 in for the time. And if that statement is true, what's c? 1. Okay, so my answer really is theta as a function of time is 2t cubed plus 5t plus 1. So when you're going backwards, you always get an infinite number of right answers unless they give you a little bit more intelligence. They say, oh, when t equals 0, this is what it was. They give you some initial conditions. Or they give you some middling conditions. In this case, it was at t equals 1 second, theta equals this. Okay? They got to give you a little bit more information. Otherwise, you have an infinite number of right answers. And that's, you know, physically, that's difficult to deal with. Here's your paper, Doc. All right. Example 3. Unless there's questions, stop me. Somebody stop me if I'm going crazy.
Not yet.
Not yet. All right, I'm going to take it off of drawing mode. I'm going to advance one, put it back on drawing. I should have left myself some more room here. I'm going to have to apologize to whomever is watching this video. Okay. Saw blade. Accelerated from the low speed of 20 revolutions per second to the high speed in 5 seconds at an angular acceleration of 61 radians per second squared. What's the high speed? And then, how many revolutions does the blade make during the acceleration? Okay, so here we go. Am I back to drawing mode here? Oh yeah, good. All right, so saw blades accelerated from the low speed. Okay, so omega final, I beg your pardon. See, I messed up right away. Let's try that again. Okay, omega initial is the low speed. We'll call it 20 revolutions per second. Check out the units. Not so happy, right? The acceleration is 61 radians per second squared. Omega final, that's what we're trying to find. Delta t, we know this change occurs in 5 seconds. Can we do this? Absolutely. For we know that omega final is omega initial plus alpha delta t from that big giant thing I showed you earlier. What are we going to have to do before we can put our numbers into this very distinguished equation?
Convert omega initial to meters per second.
Yeah, we want omega initial to be in what?
Meters per second.
In what?
Radians.
Ah, thank you, Jake. Radians per second. I'm hallucinating. Kellen just gave you the look of death. Oh my gosh. Kellen, is everything okay? You're just disappointed with him, aren't you? Mm-hmm. Yeah, I'm sorry. Okay, so if I want to change revolutions to radians, what's the conversion? 1 revolution equals 2 pi radians, yes? 2 pi radians. Once around. So if I multiply by 2 pi radians, multiply that guy by 2 pi, I'm going to get 40 pi radians per second. Now, whatever you do, please do not put your final answer in terms of pi. Punch it out. There might be some times in multiple choice questions where they give you answers as multiples of pi. That's fine. But when you're doing a formal problem like this, please punch out when you get to the final answer. So I'm going to go ahead and put it in here and say, okay, this is going to be 40 pi radians plus an alpha of 61 radians per second squared times 5 seconds.
Isn't it 40 pi radians per second?
No, no, ma'am. I'm going to take this 20 revolutions per second. I'm going to multiply it by 2 pi radians per revolution and get 40 pi. Oh, I see what you're saying. You want the units corrected. I'm sorry. I thought you thought the number was wrong. Nope, you're absolutely right. You're right. That should be 40 pi radians per second. Thank you, ma'am. You're not going crazy. I made a mistake. I just couldn't see it. All right. So, punchity punch punch. We got 40 pi plus 61 times 5. And I'm looking at 430 radians per second. Okay? If they wanted it in revolutions per second, it's a simple conversion again. Divide by 2 pi. And if they insisted, we could say, oh, okay, it's 69 revolutions per second. 68.5, unfortunately, rounds to 69 revolutions a second. Okay? RPS. Probably, if you were looking at an actual saw, they probably wanted RPM, revolutions per minute. But we're okay with it. Okay, last thing on this problem, it says, how many revolutions does the blade make during this acceleration? What are we trying to find? What are they asking for? Are they asking for omega, alpha, theta, delta theta? What's going on? They're asking for the acceleration? They're saying, how many revolutions does it make? Yeah, they're saying, how far does it turn, right? So, yeah, delta theta is what we're after. And we've got an app for that. Delta theta is omega naught delta t plus 1/2 alpha delta t squared. And the reason I went that direction was we know delta t. It's not time independent. We're okay. We can do this. So, I've got 40 pi radians per second here. Multiplied by 5 seconds plus 1/2 of 61 radians per second squared times 5 seconds squared. So part of the problem here is figuring out what you're trying to find. What are they giving you? What are you trying to find? And the problem also is the units. You know, it could be revolutions. It could be revolutions per second. They could give it to you in degrees or degrees per second. And it's all the same stuff. So let's punch it through. 40 times pi times 5 plus 0.5 of 61 times 5 squared. And I'm getting 1,390 radians. Unrounded quite yet. 1390. Okay, radians on the bottom, revolutions on the top. 1 revolution, 2 pi radians. Divide by 2 pi. $221 revolutions. So 220. All right. Again, apologize for the stuff being all cramped up there. I should have made that diagram a little smaller. It's a pretty useless waste of space there, a big old saw blade. But I usually use the board and not the whiteboard or the magic board. How you doing?
I have a question.
Yes, sir.
When I divide by 2, 5, it makes my number go up.
Okay, what you got to be careful of is when you divide by 2 pi, you're dividing by both 2 and pi. So what you're doing is you're dividing by pi and then, dividing by 2 and multiplying by pi. So put parentheses around your denominator.
Are you in radians?
In other words, no, you don't have to be in radians, or we're not doing any cosines or sines here. His problem is he's got to cover his bottom. Okay, got to put parentheses around the denominator. How'd you interpret that, Stephen?
Same on calendar.
Got it. Okay. Now, what we're going to do next is, let's see, I'm going to clear all this out, and I'm going to go to drawing mode again. And I'm not going to do this particular example, I'm afraid. I'm going to go to drawing mode and a clear board. Okay. Part 3. Rotational kinetic energy. Okay. Now, this starts innocently enough as rotational kinetic energy and leads us to some pretty strange stuff. Okay? Check this out. If I take this wheel and I just grab it by the edge and I throw it across the room and hopefully miss Allie, it'll have lots of kinetic energy because kinetic energy is the energy of motion. If something's moving and it's got mass, it's got kinetic energy. Question. Just take the wheel and spin it. Is there kinetic energy? There's definitely motion there. If I take a little chunk of this rubber on the outside, just concentrate on that. It's got a velocity, it's got a mass. Oh yeah, it's definitely kinetic energy all over the place. So, if we kind of start off in a kind of a logical approach to this, and we say, okay, let's say I've got this wheel, and it's got an axle on it so it can rotate, and it's made up of trillions upon trillions of little particles. Every little particle has mass. As it spins around, every little particle has a velocity. Okay? Every little particle has a radius, a distance from the center. Add up the kinetic energies of all those little particles, and I will have the kinetic energy of this wheel. Sounds pretty tedious. That's not the way we'll do it, but that's the way we'll start. We'll say, okay, the kinetic energy of this wheel is the sum from I equals 1 to n, where n is the number of particles that make up the wheel, so from 1 to 97 trillion. And I'm going to add up all their kinetic energies. So kinetic energy is 1/2 mv squared. So I'm going to take all their little masses and all their little velocities, and I'm going to square the velocity, multiply by 1/2, and I will have the kinetic energy of the whole thing. Okay? Very impractical method of finding the kinetic energy of something, but that would work. Now, question. All these little guys have different velocities because they all have different distances from the center. Now, a little particle here toward the center is going to have a smaller v than a particle toward the outside. You're all okay with that? There's a great Calvin and Hobbes cartoon where he spends the whole night thinking about this. Okay? It's like, it's weird. Now, the reason that bothers us sometimes is because these all share one thing in common. This little particle, when he goes around once, this little particle has gone around once. That is, when this guy has done 2 pi radians, this little guy has done 2 pi radians in the same exact time. They all may have different v's, but they all have the same what? Dun, dun, dun. They all have the same theta, okay. They all go around the same theta, and they all do it in the same time, right?
The same omega.
They all have the same omega. So if this guy's going around at 18 radians per second, this little guy in the inside is going around at 18 radians per second, yes? They're both undergoing the same amount of theta in the same amount of time. By definition, they all have the same omega. Oh my gosh. Now, take a look at this. Remember that omega is V over R, or V is omega times R. So I can rewrite this puppy up here. I can say, all right, this is the summation of 1/2 m omega squared R squared. Now, I didn't put a little I there on the omega because they all have the same omega. I had to put a little I on the m because they may all have different masses. I had to put an I on the R because they definitely have different radii. You know, there may be some that have the same radii, but the radius varies from particle to particle. So because the omega and the 1/2 are constants, I can pull them out. Yes, sir?
Would it be omega to the 4?
It would not, sir, because remember V is squared.
Yeah.
So if I square omega times R, I'm going to get omega squared R squared. It's no problem. All right. So I'm going to do something here which is a little weird. I'm going to pull out the 1/2. There we go. And I'm going to pull out the omega, but I'm going to leave it behind here. I'll show you what I mean by that. So what I have here is 1/2 goofy thing in brackets times omega squared. Okay, now if you go back a couple pages in your notes, remember that page a few minutes ago where we had the chasm between linear and rotational worlds. And it was theta, it was x, v, a. It was theta, omega, alpha. And I had all the equations. And everybody had their evil twin over on the other side, right?
Mm-hmm.
The same is true for kinetic energy. On this side, in the linear world, kinetic energy is 1/2 mv squared. On the other side, kinetic energy is 1/2 something weird times rotational velocity squared. So check it out. We've got 1/2, 1/2. We've got linear inertia, the mass, how much inertia something has. We've got this weird quantity called rotational inertia now. And then we've got linear velocity squared, and on the other side we have rotational velocity squared. So what I'm claiming here is that this weird thing in the middle has something to do with the inertia of the object. So the rotational inertia of the object is the sum of all the MR squareds. So we're going to calculate this tomorrow, but what I want you to look at right now is to notice that this rotational inertia quantity, whatever the heck this is, depends on the mass of the object, but it also depends on where that mass is located within the object. Okay? So, for example, I run over here and I grab these two rods. And I have Jake stand up and grab these rods at their centers. And just kind of heft them up and down a little bit. They have, you want to be right at the center here, Doc, so perfect. Okay. They have exactly the same mass. So they have the exact amount of inertia. If he tries to accelerate these things linearly, it's going to take the same amount of force to give it the same acceleration. Now what I want you to do is put your arms out a little bit. You might have to rotate. And then, without knocking your coffee cup over, try taking one of them and give it a little twisty, and do that same with the other one. Are they the same? Is one a little tougher, harder to accelerate than the other? That one's harder to accelerate. Okay? I've got another set over here. Bree, stand up. Grab them in the center. do the same thing. They have the same exact M. So what's different about it? Where the mass is located. So here is the non-cheating version. This is the X-ray eyes version. This is what they've got. This guy is a metal rod with two 500-gram masses on it. This is the same metal rod with two 500. Hand that to Lucas. Let him play. With the same 500-gram masses on it. If I try to accelerate this guy, it's like, walk in the park. Try to accelerate this guy, it's like, you just fucking jigga booger, what I got. Right? Yeah. The mass is located further out. Okay? Take a look at this. I've got two round things. Same radius, same mass. I can prove it to you if I put them on a masser, but we don't have time. Try to accelerate this guy. Walk in the park. His mass is distributed throughout the entire object. This guy, all the mass is located on the edges. Oh, a little tougher. Okay? So there's this weird quantity now that shows up, and it's extremely useful in our daily lives and in gyroscopes and all kinds of crazy stuff. I mean, we tried once to make a robot stand up straight, so we used a gyroscope. And that was this property we were using. So we'll do that tomorrow. Your assignment's on the board. Those are problems, not questions. Have a great day.
And none of those are kinetic energy.
Nope, none of them are kinetic energy.